let's start. So in my research, I work on human-robot collaboration, or in any setting where humans and robots coexist. So sometimes these are things where humans and robots are explicitly collaborating, like maybe they're stacking a burger together. In this case, of course, it's a toy burger, or they're building a structure together. Or it can be even more involved collaboration, things like assistive robotics, or these assistive devices that help people walk, like let's say people with stroke walk. Or it can be much larger multi-agent settings like traffic, where a number of autonomous cars are trying to interact with a lot of human-driven cars. And in all these settings, it would be really useful if the robots can anticipate what the humans want or what the human is going to do, because in that case, they can better optimize the objectives. Like in human-robot collaboration, they can increase efficiency. In assistive robotics, they can increase safety and comfort of the user. Or in the multi-agent setting scenario, we could minimize the congestion on the traffic. So how can we make these robots learn the behavior of the humans or any other agent that they are interacting with? And perhaps machine learning is the solution. I like to start my talks with this slide to show kind of the contrast between different domains. For example, GPT-4, we don't even know how much text it was used. The estimates are like on the level of petabytes. And with a petabyte of text, let's say, they were able to generate this language model that can produce human-like texts. Or ImageNet, an older version, had 14 million images, and it led to image recognition at the level of human proficiency. Or we can take AlphaZero. It played 44 million chess games on its own, and it became a superhuman chess engine just in one day. Right? But what is the state of robotics? So the state of robot learning, it kind of looks like this. This is, of course, a few years ago. This is Google's ARM farm. And in the talk in the morning, actually, Shenlong mentioned like how this is a failed approach of like we can try to collect just tons of data and we are going to do a maybe like robot foundation model. Because the problem is, like if you compare this with 44 millions of chess games, this is a very small amount of data, right? And the problem gets more difficult when we have a human in the loop. Because now we need a human to interact with this robot. Like the human needs to sit in front of this robot and control the robot, or maybe just interact with the robot. So we need to ensure their safety. And now on top of the cost of the robot, now there's a cost because of the presence of the human in the scene. Right? And that's too expensive. So in my group at USC, we try to tackle this problem by taking different approaches. One approach that I'm really excited about is to diversify the type of feedback that we can collect from humans. Right? So we look at humans' gaze, interventions, preferences, demonstrations, facial expressions, gestures. So everything that we can learn from a human, we try to learn from them. And our ultimate goal is to develop algorithms such that we can be as efficient as a human, or maybe even more efficient than them while learning new tasks. So if a human is able to learn a task by just watching someone else do it once, I want the robot to have the same capability. The robot should just watch something being done from a human, and it should be able to do that itself.
So do you mind the interruption during the talk?
No, I don't mind. Yes.
Oh, like with the slide before. So like I find this interesting. I've heard this point several times, and like, but a counterpoint usually is the fact that with LLMs, like okay, we use them as chatbot, even though there is no human in the pre-training state.
Right.
Right. So why should it be different for robot? We just kind of train robot with data they collect themselves, maybe robot versus robot, and then we go the generalized to human.
Right. So I think there's an important difference. So in the case of language, yes, like an LLM can replace a human for language-related tasks. And in many cases, that just works fine. Robotics is a lot more difficult than that. One of the reasons is that robotics is a very high-dimensional problem as opposed to a language problem. Like in language, it's a one-dimensional problem. You are predicting the next word. I mean, there are many candidates. I'm not saying it's an easy task. But it's a one-dimensional problem. In the case of robotics, like even this, like it's a simple robot arm like this, it has like 6 or 7 degrees of freedom. So it's already at least 6-7 degree dimensional problem. So we need a lot more data than the case of language. And I think Ken Goldberg had this comparison of like this is the amount of data that Pi0 collected. This is the amount of data that QN used. And like if you do the scaling, it's like it's gonna take 120,000 years was his conclusion, I think.
For like, I have a complaint with this, and I also mentioned it to Ken. The fact that it just depends on the effective dimension of the data.
Right.
It depends on the nature of the problem.
Right.
Not really on the dimensionality of the data. Like if you have to
do
something
that's true.
like very easy, like detect a blue dot into an image. The image is high dimensional, but the task is very easy, so you can get it done.
That's true. I mean, we have a lot of redundancy in our movements. Like there are many body poses that I probably never did in my life and will probably never do. But that being said, I think even the effective dimensionality, I mean, it's going to be higher than 1. And I think it's still a more complex problem than the language problem. Plus, like doing what you suggested requires being able to simulate a human or like having a very realistic robot that more behaves like a human. Like from a theoretical perspective, I think it's a solution, but I don't see it as a feasible solution. It seems too futuristic to me. I don't think we are anywhere close to having that amount of data. So yeah, as I was saying, in my lab, we try to diversify the type of feedback we can learn from, we can get from humans, and our goal is to achieve human-level efficiency in learning new tasks. In my talk today, I will present 3 different projects that we conducted with this purpose in mind. First, I'm going to talk about a project where we try to learn from humans' eye gaze. So the robot is learning something, and the human is watching the robot learn something. Can we track their eye gaze and extract some information from this gaze tracking? Second, I'm going to talk about some learning from language, but specifically comparative language. So I'll have a lot of background in preference-based learning, and now with all these like learning from language, I was like, okay, there's actually a nice connection here. Let's try to do something in the intersection of preference-based learning and learning from language. So I'm going to talk about comparative language. And finally, I will talk about how we can make robots learn from either a single demonstration or a single instruction of the task. Okay, let's start with eye gaze. So to begin with, I want you to watch this 9-second video of this robot opening this drawer. Like you don't need to quantify its success or anything. We are just watching the robot open this drawer. Okay. Now, while watching this video, like what did you pay attention to? For example, did you pay attention to whether the robot had a shadow or not? Or did you pay attention to the texture of the table? Like the answer is usually no, because in the beginning, I told you this is a video of a robot opening a drawer. So what you pay attention to is usually the end effector of the robot, as well as the handle of the drawer, right? But our robots are not necessarily doing the same thing. Like while they are doing reinforcement learning, we just give them this image, and we expect them to learn what they should do from the image. Right? But this image has a lot of parts that are irrelevant to the task. Right? Versus as humans, we have this prior that when we look at this, we look at the end effector and the drawer and the handle of the drawer, because we know those are the important parts in the task. So we ask, like, wouldn't it be nice if we could somehow tell this to the robots? Like, these are the important things, just focus on these things. And maybe in that way, we can get rid of a lot of exploration that's happening in reinforcement learning, right? So the idea is that we want to track the human's eye gaze. And arguably, they're going to be paying attention to the end effector and the handle. And we will give that information to the robot. In reality, we are cheating a little bit. So instead of tracking their eye gaze, we have this interface. We ask the users what is important in this task, and they use their mouse to like create this heat map. So depending on how long they click, we create this heat map, and like in this case, the end effector and the handle are the most important. So they click that region more, and then the rest of the arm, they just maybe hovered it once or twice. Okay. And we do this, but of course it would be very unfair if I just call this section eye gaze while we are doing this. So now we have some extra studies where we are trying to actually use eye gaze. We have this gaze tracker that tracks the human's eye gaze on a screen, and we are doing some experiments on this. For example, here is one from the Atari domain. I don't know if it's visible. There's a red dot here. So that red dot is going to show you where the human is looking at. So when I play the video, you can often see the human is going to be looking at the enemies and sometimes the ship itself because of localization. So I think like we have some good qualitative arguments to make about like how human eye gaze really correlates with the saliency in the task. And there are some like neuroscience studies that suggest this as well. And more recently, we got these Project Aria glasses from Meta. And now we can do this in the 3D world as well. So it doesn't have to be on a screen. This is eyes of one of my master's students. And he is doing this. Is there a way to turn off these lights? Maybe, I don't know if videos are going to be visible.
I want to say this.
Oh, it's there.
Somewhere here.
Yeah, if it's it's fine. It's fine. It's not bad.
Also, can you close the yeah?
Oh no. Okay. I hope people on Zoom can still hear me. I'm going to share the screen again. Okay, yeah, here. Okay, yeah, in these videos. Okay, here we go. The blue point is the eye gaze of the student, and he's doing some like different tasks as like folding clothes or cutting a piece of paper. And you can again see that eye gaze really correlates with what is important in the task. But for the results that I'm going to show you, we use this interface. Those experiments with the glasses, they're still ongoing. Okay. So
time varying dynamics to the ideal in this case. Right? It's not as though you have for each frame the annotation of the important things. It's more like at a task level.
Yes. So we just get like one frame, and then we tell the task to the user, and they annotate it for us.
Okay, but do you do this for every frame, or do you do this?
No, and I'm going to talk about that. Okay. Yes. So yeah, what we want to do is like this is again the reinforcement learning loop. We have the image from the environment, and we were giving it to the robot. Now, in addition to the image, we also want to give the saliency information. So we are going to make the human watch the process, and at every frame, like if this was eye gaze, we would just give it to the robot, right? But of course, with the interface that we are using, this is way too expensive because we cannot ask the human to annotate every single frame. But luckily, computer vision people figured that out for us. There is this model called PicaNet, and what it was trained to do is like you give an image, it gives you the saliency map of that image on some image recognition tasks. And this was like pre-trained. So what we do is we get only 24 frames from our task, and we fine-tune this PicaNet model with those 24 frames. And it gives us pretty robust estimations of what the human would pay attention to. So in the loop, we basically replace the human with another AI model, in this case PicaNet, that gives us the predicted saliency, and then we feed it to the robot. And how do we feed it? There are two different ways that we experimented with. One is we simply give it as an additional channel. So it's like, let's say we have a CNN policy. Usually the image is like RGB, right? We add an additional channel, so it's now RGB saliency. So we are essentially making the input space larger, but because this additional channel has valuable information about the task, it actually improves the data efficiency in these different meta-world tasks. And this is just like some model-free reinforcement learning here. But there is actually a better way of doing it, which is we use this multimodal masked autoencoder. So what it does is, without the multimodal part, given an image, it masks some part of the image. It learns an embedding such that this embedding is going to reconstruct the masked parts of the image. So it kind of forces the embedding to learn the image in a way that it should be able to reconstruct the image given a small number of patches, right? In the multimodal version, in addition to the image, now we have the saliency map, the saliency prediction, and they are masked, and each of the embeddings contribute to the reconstruction objective. And this architecture has a nice property, which is like we can do this in training, but then later in deployment, let's say we lost access to saliency. So we can, like this architecture will still operate if it's just the image input without the saliency. But of course, we have picanet, so we don't need to do that. Like picanet already estimates the saliency for us, so we can keep giving this as an input.
Saliency is given by human or by the model?
Yeah, so initially it's the human. We only collect 24 frames. We fine-tune the picanet with those 24 frames, and then now picanet gives the saliency.
Task. When you say for 24 frames, it's for each task, right?
This is all single task.
Yeah. Okay. Yeah. So for a single task.
For a single task, 24 frames.
24 yes. frames and collected across like some episodes or something like that.
Randomly selected frames from an episode. Yes.
Okay. And I assume that when you showed that effect on the previous slide, that you compared also against a baseline that was not pre-trained, not fine-tuned on the human annotation, like just the saliency straight off the bat from the original model. Is that right?
Wait, say the comparison again. Which baseline?
From the original model without any human annotation fine-tuning.
Oh, right. We don't have that comparison here, but that wasn't performing as good because the human saliency is slightly different from the saliency of the. I mean, not slightly, but
other
different.
Model is not conditioned on the task. It's just saliency at like a task independent.
Yeah, I think the way they trained it is some image recognition task. So I would imagine it would focus on the key points of the image.
So if you would segment the robot, with SAM or like whatnot, this will not work as well as for like human attention.
Yeah, I think the usefulness of human attention mainly comes from the fact that the human knows the task and pays attention to that part of the image. Like perhaps you could try to do some like segmentation plus like do some LLM pre-processing to get the relevant segments of the image. That could help, but I think there's still more information in human saliency because, for example, like if we think of this object, like this monitor here, and if the task is to lift this, the human knows that I need to maybe hold it here or here to lift it, but like not here, right? Versus if you do segmentation, you are getting the entire object. So there is less information in segmentation than human attention. Any other questions?
On the high gaze, have you found, like with the human experiment, that like the gaze is rather towards what will be important for the future,
yes,
and not what is important right now?
Yes,
because I guess humans have a very good predictive model. So
yeah, that's correct. Especially for like when the robot is moving, they usually tend to look at maybe like where the robot is going to be in like next second or next 2 seconds. In this work, like we didn't account for that, but I know like in, for example, some autonomous driving works, like they try to account for that difference. But yeah, in this case, we didn't.
Dana Ballard in the 90s had a paper on that, showing that gaze tracking with humans in household kitchen tasks. They usually move on to the next task before they complete the task.
Yeah, so we use this multimodal masked autoencoder to learn these embeddings from both the salience and the image, and then we get those embeddings to the reinforcement learning on top of those embeddings, and this actually gives the best results across all.
The pre-trained, the transformer, the reconstruction target still remains as this image target, right? So it's not
both of them. So the input is both of them, the output is both of them. So like we need to reconstruct both the saliency and the image.
And this reconstruction target is used for the is it used the image?
No, this is only for representation learning. After we learn this transformer encoder, we discard the decoders, and we only use those representations to train a policy. Yeah, perhaps you could do something iterative because arguably the robot trajectory is going to change. So you do one, train the policy a little bit, do it again. So yeah, with this multimodal masked autoencoders, we were able to get the highest data efficiency. So the key takeaway is that human saliency, it carries information about what is important and what is not in the scene or in the task, and feeding this directly to the robots without doing anything smart, actually, it improves the sample efficiency of the robots learning, in this case, reinforcement learning. But of course, reinforcement learning is not the only way we teach robots. There is this other, I guess, big model, imitation learning. And imitation learning has been around for more than 35 years. And one real good reason to use imitation learning, it's often much more data efficient than reinforcement learning, which allows us to do things on a real robot. So all the results I showed so far, it was on simulation. But actually, with imitation learning, we were able to do some real robot experiments. So in this case, a human is controlling the robot. We are also again, using their saliency information, and you can see without saliency and with saliency, like the success rate increases. Yeah, and as I was saying, like imitation learning, it's known to be more sample efficient than reinforcement learning, and people have used it in many applications. So here I'm listing some in the autonomous driving domain. But if you look at all these papers, there is usually some additional component on top of imitation learning. It's never like we collect a lot of human data, we train an imitation learning policy, and it works. Like, for example, the work in the middle, it belongs to us from 5 years ago, and we had to learn multiple different policies, and then we were trying to optimally switch between them. But like, what is the reason? Like, humans are able to drive cars, and why can't we just look at how they drive and just imitate what they're doing? Right? And one of the reasons for this is in many robotics tasks, the human demonstrations are actually not optimal. They're suboptimal, and the robots can learn to, I guess, optimize for those suboptimalities. So here are some reasons why human demonstrations tend to be suboptimal. So first of all, many of these robots have high degrees of freedom, and it's very difficult for humans to control them. Here, this is my former lab mate, Andy, and Andy has a lot of experience with the fetch robots, and he's trying to control the robot to reach the notebook, but he's having a hard time because, first of all, this robot has 7 degrees of freedom, and Andy is trying to use a keyboard to control it. So it's very limited controllers trying to control a robot that has high degrees of freedom, right? So it's a problem with the controller in this case, and the limitations that we have as humans in terms of how many degrees of freedom we can control at a time. Or there's this work from Berkeley where they showed humans do not like their own demonstrations. They think it's too aggressive. Like, they did this experiment, like they collected some data from humans. 1 week later, they showed their policy to them, and they said this is too aggressive. And it's because usually the way we want to do things do not match our own evaluations. You can think of it as like driving yourself versus being in a car that someone else drives is different, right? In the second case, you usually want something maybe like more conservative driving policy. Okay, and then in another work, we showed that humans take consistently suboptimal decisions when they encounter situations that involve risk. And this is a known result in behavioral economics. We just showed the same thing holds in robotics as well. Okay. So then the question becomes, okay, if the humans are not giving good demonstrations, like what can we do? Like, if the demonstration is good, how are we supposed to learn from it? So we decided, okay, maybe we need different types of feedback. One idea is that maybe the robot should do something, and then the human should evaluate how good or how close to optimal that trajectory is, right? But often humans provide unreliable information in this kind of scenario as well. And it may not be obvious why. So I like asking this seemingly unrelated question, which is, how dark is this blue? Not dark. It depends. Okay. Yeah, usually people, well, some people try to like quantify it. They say like 2 out of 5, or yeah, it's like some people say not very dark, some people say kinda dark, but it's a very ambiguous type of feedback. And if you think of it, it's the same situation here. Like, the robot does something, and then we ask the user how good that robot trajectory was. They'll say things like, it was kinda good, or like it reached the target a little bit. But I don't know how to get this feedback and transform it into something that the robot can learn from, right? Maybe like we can try to do some, LLM pre-processing to give the sentence, get a reward signal, but it's also going to be very like different between different people. So it's also going to be difficult to normalize, right? Instead, we are better at comparing things. So if I introduce a second color and ask which blue is darker, now like everyone gives the same feedback and it becomes very consistent, and it's some kind of signal that I can use to train the robot, right? So our idea is to have the robot leverage this kind of feedback and learn from such comparative data. So in the second part of the talk, I'm going to talk about how we use comparative language to learn the objectives from humans. Before starting on comparative language, let me briefly mention learning from comparisons, and as that's the mainstream approach now. And in case you're not familiar, this is like a very quick course on this. So in learning from comparisons, the robot shows two different trajectories for the same task, and we ask the user whether they prefer trajectory A or trajectory B, right? And their response gives us information about what the human wants. Okay? And of course, this is not just a robotics thing. Like if you are using ChatGPT, you may have seen prompts like this, like you ask a question and it generates two different responses for you. And then it asks like which one you prefer. If you give a response, maybe they're using it to fine tune their model. And it has also been used in some recommendation systems. This is a startup called Belly. They have this app. They make restaurant recommendations. So every time you visit a restaurant, it asks you to compare it to the previous restaurants you have been. And in that way, they claim that feedback is more reliable than you just clicking one of the 5 stars. So mathematically, what's happening? We have 2 trajectories, or in the other cases, 2 items, xi A and xi B. And there's a response by the human, which is a binary variable q. So q is a binary variable that indicates whether you preferred A or B. And the assumption is that the robot should optimize some reward function R. That is what the human is making its judgments based on. And this reward function is parameterized by some reward function parameters W. And what we are trying to learn is those parameters W. And how do we do this? One approach is to go Bayesian. So we are going to learn a posterior of the reward function parameters W given all the comparison data. And then we will maybe like get the maximizer of that W. So in the Bayesian approach, we write this as like some prior times likelihood. The prior here, if you have some information about the task or some domain knowledge, you put it into the prior. But the more interesting term is the likelihood, because that's how we are going to get the comparison data into the model. And we make 2 assumptions here. One is we assume each comparative feedback is conditionally independent from each other. So if you reply the question, if you answer the question, and then you answer a second question, the answer to the second question is independent from the first question, right? And given the task or the reward function is the same, I think it's a reasonable assumption. And the second assumption is that each comparative feedback comes from this Bradley-Terry model, right? So what it means is that if you are choosing between trajectory A and B, the probability that you choose trajectory A is proportional to the exponential of its reward. So the more the difference, the more likely you are to choose the trajectory A. Okay. But of course, like again, assuming like humans are not just noisily optimal decision makers, there's a lot of criticism about this model. But it's not just the optimality of the human. I think this learning from comparisons has a lot of drawbacks. For example, okay, before that example, here is a result that we where we compared just learning from demonstrations plus or versus some demonstrations plus comparisons. And the nice thing here is that because demonstrations are hard to give, the robot actually fails to achieve the task with 5 demonstrations, versus if you do 1 demonstration plus fine-tuning with 15 comparisons, it reached the target. Of course, like you can question like why 4 demonstrations equals 15 comparisons. That was giving the exact same, well, almost exact same convergence rate in simulation when we simulated humans as noisily optimal decision makers. So we use the same numbers, but in reality, humans are not noisily optimal decision makers, and that's why we see this difference in performance. Okay. But yeah, as a
performance if you tune the prior.
well, if we tune the prior, we can do it for both of them, right? Yeah. So I think it's like a same level thing. Yeah. Yeah, but as I was saying, learning from comparisons has many drawbacks. For example, one of them is comparisons take too long. So the way it works is like the robot in a lab, the robot is going to do something, and then a student is going to go and then press some buttons. The robot is going to reset. In some cases, the student will also need to reset the environment. And then the robot is going to do a second trajectory. The student is again going to go reset the trajectory. And then at the end, the subject is going to give a response, right? So to give that comparison feedback, we need to watch the robot do the task twice. And at the end, what we give is a comparison between A and B. So information theoretically, the most information you can get from such a comparison is just 1 bit. Right? So we are waiting all that time to make a very small contribution to the robot's model. And
the way that you're using the comparison data, are you using it, do the trajectories being compared have to be online?
No, they don't have to be online.
So you can choose to keep all the old trajectories around and keep reusing them for comparisons or like rank them or something.
Yep.
It's
Yeah.
a more efficient way to get the comparison data.
You can do those, and like in fact, like I did a lot of like active learning type of research where you try to find the best trajectories to show so that you can get most feedback. But still, the upper limit is like with pairwise comparisons, the upper limit is still 1 bit. And compared to like how large these models are, 1 bit is not a lot of information. And again, like this is not just a robotics problem. Like if I'm lazy enough to write my own emails, am I really going to read these 2 essays and choose which one is better? It's not time efficient at all, right? And another reason why comparisons are not great is it doesn't convey any information about why I preferred what I preferred. So like here, if the goal is to reach this red ball, of course, I'm going to select the trajectory on the right. But does the robot know I choose it because it reached the red ball better? Like it can think, okay, Erdem wants the end effector to be close to the table. Or maybe Erdem is trying to reach the obstacle, the blue box there. Right? Like, so instead of binary comparisons, like, wouldn't it be nice if we could just say, like, we tell the robot, move closer to the red ball, or just move faster, and then the robot somehow understood this and adapted its behavior. So the second part, this learning from comparative language, that's what we are trying to do. So what is comparative language? Now the robot is going to show a single trajectory to a human, and the human is going to give some language feedback that makes a comparison. That's what I meant by comparative language. So the user is going to say something like, move closer to the cube. So there's a reference trajectory, and the human is making a comparison with respect to that reference trajectory. Now, the challenge is, of course, how are we going to make the robot understand that language utterance and update its behavior? Our idea is to train a shared latent space between the robot's trajectories and the language utterances we can give. So you can think of this similar to machine translation. Like in machine translation, like you have these English sentence, Vietnamese sentence, Turkish sentence, and if it's the same sentence, you try to map them into the same latent space, such that from that latent space you can translate it to any language. Right? Now, instead of language, what we are going to have is this comparative language feedback and the trajectories for the robot. So how is that going to work? For that, we will first collect some data set, and this data set is going to consist of, again, a pair of trajectories, and the user, a human annotation of how these trajectories compare with each other with respect to any of the aspects. Right? And we are doing this only once, so this is pre-training. After we do this pre-training once, we will be able to learn reward functions of different users without repeating this part. So in this case, like we show 2 trajectories, A and B, maybe the user says something like trajectory B moves faster than trajectory A. And again, this has nothing to do with the user's preference. The user is just giving us a fact about the comparison. Right? And of course, there are many different ways of saying trajectory B moves faster than trajectory A. So what we do is we augment the data set with language model. So we give this sentence and language model generates 100 different ways of saying the same thing. And then having this data set, now we are going to train the shared latent space. For that, we are going to encode the language utterance, like move faster, with a pre-trained model like T5. So that gives us a vector of that language utterance. And then we will train these encoders for the trajectories. And this is where we need to align the feedback. So we have the representation of trajectory A as phi A and trajectory B as phi B. And I know that this language utterance compares these two trajectories. So I want this difference to match with that language utterance. Okay. So that's where we create this loss function that tries to make this alignment between the difference of trajectory embeddings and language utterance. Does that make sense?
The average of the per frame embedding?
Yes, we really did average. It would be, I think the performance would be better if we use the transformer and like encode the entire sequence, but that would require a lot more data. And with limited data, we found that transformers quickly overfit, so we did this.
Yeah, it seems like things like faster and slower would be particularly hard to capture.
Yep.
With frame average.
Right. Yeah, that's correct. Yeah. So we did this alignment with this approach, and then we looked at how good we can predict the user's feedback in terms of like when they say move faster, do we actually predict they said move faster or do we predict move slower? So like 50% would be the random baseline, and we are way above that. So we said, okay, there is some alignment between trajectory differences and language now. Makes sense?
What's the space of different comparative aside from like speed or with a couple other things?
Right. So I don't remember the full list, but things that are like, so in this environment, we have this like distance to the cube, distance to the bottle, distance to the table, the speed of the robot, the height of the robot's movement. Have anything? Oh, and then there was something about how high the objects go, like especially like if you are picking them or if you are hitting them. That was another feature, but yeah, those kind of things that humans can easily infer from the video.
That initial set property computation that generates that we user study provide.
That was, yeah, this part is by authors. And then later when we interact with the robot, it's a user study that are not authors.
Okay. Were the participants in that user study then instructed to use comparative language, or what was, from an experimental design perspective, what was instructed?
They were instructed to use comparative language. They were not told anything about what feature the robot is able to understand.
Were they given examples of what?
Yeah, we gave examples, yes.
That they have the same number of steps. For example, here you show like T minus 1.
Right.
It's a T steps. How could I compare like these two motions if they have the same time steps?
Yeah, we are not assuming that simply because we are taking an average at the end anyway. But depending on the architecture you use, in some cases you may need to assume that. But in our case, we didn't. So this is just a note. Like I could use a different notation here. We didn't make that assumption. Yeah.
The negation of commands captured in this framework and the sense of comparing trajectory A, B, and reversing the order.
Yeah, so okay, there I think sometimes like saying B moves faster than A, like GPT already gives you like A moves slower than B. So in that sense, we are kind of forcing the pre-training to do that, but we are not explicitly encoding the fact that fast and slow are just the exact opposite things. But by doing this augmentation, I think we are kind of encouraging the pre-training to have that property. Okay.
One more question. Sorry.
Yeah.
There's been a lot, but things like faster and slower are indeed very objective things.
Yep.
But there might be things like, this is a smoother motion or something like that, or this is a more elegant motion. Like at some point you have to constrain what the user is saying.
Yep.
Or do you not? Do you just let it be very freeform?
I think smoothness is also kind of objective, but yeah, I see the high level comment. I think yes, in an actual use case, you would constrain the human to give feedback about the features that were seen during pre-training. Again, we didn't do that, and it still worked fine. But arguably, like in our tasks, maybe there was nothing to worry about, like the aesthetics of the trajectory. Like there was nothing that's so subjective. Okay. Okay. So after we do this pre-training, like why is this useful? So now we have this latent space, and in this latent space, each trajectory is a point, and each comparative language utterance is a vector. Right? Because the way we trained it is we said the difference between two trajectories is going to align with a vector. Okay, and there are different ways of using this latent space. I'm going to talk about two of them. One is we can do some trajectory, like adaptive trajectory improvement. So the robot starts with a trajectory t0, and the user says something like move slower. Now, we know what move slower means in this latent space, so we just move in that direction and find a trajectory that is close to this point, and we show it to the user. The user gives another feedback, we move in that direction, so iteratively we try to improve the trajectory. And if we look at the results, we are able to get like high, this is of course simulated humans. With real humans, we don't have real reward values. Like with simulated humans, we are able to get these like improvement over time. But one thing, of course, you'll notice is that we are not reaching the optimal performance. Like here, optimal trajectory means given the reward function, what would be the like best trajectories reward, right? And we are not reaching there. And one reason is that this feedback type is memoryless. Like the robot shows something, and I'm giving feedback only about what the robot showed me. It completely discards the previous ones, right? So sometimes there will be these cases where the robot is stuck in a loop. It's like show something, you say, like you give a feedback, it goes to another trajectory. You say something, it goes back to the previous one, and it never like gets out of that like local optima. So the second way kind of solves this. Again, there is this initial trajectory. The robot asks like, okay, this is the trajectory. What do I do now? And the human says something like move lower. Again, we know that direction, but now we do not go for the trajectory on this point. Instead, we say there is some trajectory here in this latent space. I don't need to find it. I'm just going to say in this latent space, there is this point. And I know the human prefers this point over the original point, right? Because that's what the human give feedback for. And I can add that to a preference data set, and I can do preference-based learning on this. So now I'm learning a reward function in this latent space with this comparative language feedback. So using this trajectory comparative language pair, I am learning a reward function. But that's not the end of the story, because we didn't ask the user to give feedback about the height of the robot. The user could also say, like, move faster, or the user could also say, move closer to the cube. Instead, they specifically chose to give feedback about the height of the robot. What this means is they likely thought if they give feedback about the height of the robot, it's going to lead to the highest improvement in the robot's trajectory. Mathematically, what it means is the feedback of any other sentence is going to contribute to the robot's performance less than this specific feedback. And I can write it as a preference feedback as well, because now what this is saying is this trajectory is also preferred over this trajectory. This trajectory is also preferred over this trajectory, right? So using this one comparative language, we are actually able to synthesize many different preference comparisons.
Because that you learn the latent space, right? This is a latent space, and you need to represent the distribution of the trajectories.
Right.
So do you have any constraints of a trajectory? How did you ensure that this latent space is smooth enough for to model like the full distribution of the trajectory?
Right. We are not ensuring the smoothness of it, but here the way we generate these, I guess, counterfactual feedback is that we use the set of language utterances that we use during pre-training. So it's like these are the feedback that the robot is aware of, and then we get like, okay, we know this is a valid feedback to the robot, but this didn't happen. So we say, okay, this should be better than this. So in a way, the comparative language is regulated.
Do you limit everything like to a small epsilon ball in the shared latent space? So, like you say move lower, but move lower.
How much, right?
Yeah.
Yeah. It's something we ignored in this work. We did some like preliminary studies where we tried to see if like saying move slightly lower versus move lower a lot, like if there's some like linear algebra around that. There wasn't. But I think including that magnitude is another thing that we are interested in. But with this work, we didn't have that property. Yeah, and specifically like here, I'm showing it as like a preference comparison between this point and this point. But in implementation, what we are doing is we are saying the reward has a gradient, like at this point, the reward has a gradient in this direction. And yeah, when we do this, like we have this. So this is the explicit feedback. This is the implicit feedback because of the counterfactual feedback. And if we use both of them, we get better data efficiency. Probably not surprising. And then we also compare the comparative language with just pairwise comparisons. We again get higher data efficiency. We conducted some user studies where like this Vidovex robot is trying to do some tasks in the kitchen, and humans are giving comparative language feedback by typing their feedback. And subjectively, they seem to prefer comparative language, even though this had only 10 users. So that's why these error bars are a little too large. We also recorded the time it took for users to give a comparison feedback versus a comparative language feedback. And comparative language is faster because now you are only watching one trajectory instead of two. But this doesn't give the full picture because in our user study, the users had to type their feedback. Like if we had speech to text, it would make it even faster. And in some cases, we have some examples in the paper. Some users, they decided to give like 2-sentence feedback instead of just like move faster, move slower kind of feedback. So the key takeaway from this section is that maybe pairwise comparisons are also inefficient in terms of both time and data. So instead, maybe let's try to use comparative language feedback. And it's not just a robotics thing, because it might be actually easier in other domains. For example, for pre-training in language, the data is there. Like you get any paragraph, you give it to ChatGPT and you say, make it less technical, it will do it for you. And this is the pre-training data, right? Like item 1, item 2, and the comparative language data between them. So it might be actually easier to do in other domains than robotics.
I have a question that applies both to comparative language and preference between trajectories. Have you ever encountered a situation where the person coaches the robot into a suboptimal, like global maximum? Like maybe if I'm trying to get it to grasp a pen, I have preconceived notions about what I think it will be able to do. So maybe I think that like I prefer this kind of approach to this kind of approach.
Right.
But in reality, like it would have had to do it.
Yeah.
Have you encountered that in your experiments?
Yeah, it happens. And yeah, exactly like the situations that you talk about is like robot is reaching this, but I want this. But then if it already does this, and if I say move lower, now it tries to go like below the table, and it actually like hurts the robot. So yeah, it happens, and I don't have a good solution to that. Usually what we see from most users is that they are not too ambitious. Like as soon as the robot picks up the object, they are usually happy with that. But some users, they try to optimize for the exact motion, and then sometimes we have those problems.
Okay, thank you.
Maybe let's hold for the end.
Okay.
5 more minutes for the
Oh my, okay. So now the next project in 5 minutes. So in the beginning, I promised we are going to do something that will make the robot learn from either one demonstration or one instruction, right? So now we are going to do that. Some background information. There is this model called CLIP. What it does is that if a caption belongs to an image, it maps them into the same latent space in a way that those latent embeddings are going to be close to each other. If they do not belong, it's going to be far away from each other. So we said, can we use this as a way to train our robots? So this is our standard control loop. There's an environment, there's a robot, the robot acts on the environment. Right? Let's say we have a target image. Like we have a target image of the environment that we want robot to achieve. One thing we can do is we can get the embedding of that target image, and at the end of this control loop, we can get the image of the environment, and we also encode it. And we check if these two are similar. with something as simple as cosine similarity. If they're similar, this reward is going to be high. If they're not similar, this reward is going to be low. And we are going to learn a policy with this kind of sparse feedback. With something as simple as this, like you already get some improvement in the performance, but that's not all we can do, because these clip-like models, they exist for video as well. So you don't have to use the image version of clip. Instead, like you can use this video model. And in that way, you are going to be comparing the robot's entire trajectory with the demonstration that you get. Right? So for the video model, there's this how to 100M data set. Very briefly, it's great. So there's a so people already trained these clip-like models on that data set. So we use that. And we see a huge improvement in the robot's performance because now it's not just the final state of the robot. It's about the entire trajectory. Right? OK, but that's not the end of the story, because in these clip-like models, in addition to image, or in this case video, we also have text. Right? And what it means is, instead of inputting a video and using the video encoder, I can input the text that corresponds to that video. And I know from the clip model that they have the same latent embedding, or at least similar latent embedding. So I should be able to train the robot with just this caption. Right? So I'm not even giving a demonstration now. I'm just telling robot opening a drawer. I let the robot train with this, and then the robot is going to learn opening a drawer. We did some feasibility studies, and here, like you see, the one on the left is trained with the video, the one on the right is trained with text. This is one of the rare cases. Usually video works better. In this case, text works better. And one nice thing about this is you automatically get some domain transfer, because these clip-like models, like what it learns is what is happening semantically in the video, right? So if this is the video, it's going to learn to map it to the same embedding as the caption of like opening a fridge. Okay? And then you can do things like this. So given this video, we learn this. So this is the only this is the only information that we need. We have this video, we train this. In some cases, we need to fine-tune with one demonstration, but as long as you are not doing like domain transfer, that's usually fine, because you already have that one demonstration. And then we decided to have some fun, so we decided, OK, let's take an animation video. Does it still work? It does, because again, this maps to opening a drawer. That also maps to opening a drawer. And the same thing. So yeah, with this model, we were able to get this learning from like either one instruction or one demonstration. Of course, one caveat is that we still need to do reinforcement learning in between. So it's not directly imitation learning. But it also has advantages over imitation learning, because, for example, you don't need state level information. You only need a video of the demonstration. Like you don't need action labels. You don't need state level, low level information. OK. So the key takeaway is that language instructions from humans, they're an intuitive and easy way to learn their objectives, and it enables generalizations with humans and to different tasks. Okay. And very briefly, as I said in the beginning, I'm interested in any type of human feedback that we can use to train robots, things like interventions. We have a paper coming up at ICRA, so if you're going to ICRA, find us. Or gestures, which we are still working on. And sometimes, like if the AI model, if the foundation model is advanced enough, I'm also interested in like replacing the human with a foundation model, because then we can generate tons of data and we can make it possible to learn more from that. For example, we did this work called RL-VLMF. It's a paper that I'm very proud of, because just by the acronym, you can tell what the paper is doing. I'm going to say it again. RL-VLMF. So instead of H, which is human, we put a VLM. RL-VLMF. So it's like we are doing RLHF, but VLM is giving the feedback. That is all I have, and I thank my students. And these are the students who led the works that I presented in this work, with many collaborators, of course. And I don't know if we have time, but I can take any remaining questions.
Both of you be getting kicked out of the room, so maybe up until then we have the room.
Okay.
So for the second part, are you training a latent space for each task?
Yes.
And I mean,
In this work, yes. I am not saying it's necessary, but in this work, that's what we did. Yes.
so I mean, do you expect I have a trajectory of if you train it for all the tasks? Do you expect if I do an initial trajectory, then the robot can give me an improvement of the trajectory that achieves that task?
I think such a latent representation is possible by, like, you can think of it as like in your latent embedding, you can have some part that encodes the task and some part that encodes the trajectory in that task. And if two tasks are similar, the task encoding is going to be similar. So I think you can gain some like data efficiency by training multiple tasks together. It's not something we experimented, but intuitively, I think that will be the case.
Wondering how well does a comparative language generalize to like different objects? So, for example, like during the training, the feedback you give is like move closer to the model. During execution, you're asking closer to a cube, which doesn't really appear in the training.
Oh yeah. Yeah, if it doesn't exist in the training set, it's not going to generalize. And it's mainly because we are training a trajectory encoder from scratch. So the trajectory encoder will have no idea about that object because it has never seen that. If you have enough data, you can use a VLM there, and you can fine tune the VLM, and then you may get some generalization. But the way we are doing it is not going to generalize to new objects.
The benefit was that the clip reward just has semantics, like close and door.
Right.
But my concern there is you're discarding a lot of like the low level physical information. So maybe my question here is like, how sparse is this clip reward? Do you think it's giving a lot of intermediate feedback, or then more just like a success?
It is very sparse, first of all, in the sense that you are getting a reward only at the end still. Like it compares the entire trajectory, but you get the signal at the end. So that's definitely sparse in that sense. But it is not as sparse as success failure, because depending on how close you are getting to the completed task, you can get a value that is maybe like smaller than 1, but close to 1. So it is like, it's sparse, but at least still a continuous value between 0 and 1. But it's true that you are discarding a lot of low-level information. It would be interesting and nice to have some like hybrid method that like maybe on top of this also rewards based on the low-level motions or like the mistakes the robot does.
So for the same project, the action space is trajectories?
No, we use the reward from the clip as the reinforcement learning reward, right? But then we still do reinforcement learning with the actual like action space of the robot. So it's like it's RL where the reward only comes at the end.
Yeah, but
Yes.
And then so I was curious for this. Do you see it working like for more and more complicated tasks as you arbitrarily like increase the space of commands like supervise and like the complexity of scenes that you're interacting with, like it'll improve, and the one gets bigger, then it'll keep improving, or what's the limiting factor?
Yeah, so one limiting factor is the way we have this video version of the clip model, and that was trained on this how to 100M dataset, which I skipped quickly. But that dataset is like it consists of things like, okay, crease origami, measure the length, measure blood pressure. So these are all like single tasks, right? And because of this reason, it's not going to generalize to sequential tasks. If you want to achieve sequential tasks, there are two things you can do. One is you just increase this how to 100M dataset with such tasks as well, and then you train this clip model and then do the reinforcement learning. The second way is you learn to divide the task into subtasks and then use this.
Maybe one last. Why do I've seen a lot of people look at eye gaze studies, but for something like robots, it feels like we should just be able to like point at things and you get like more precise signals. why do more people not study like a simple gesture, like pointing rather than?
Yeah, gesture point. There are some works that studied that. For example, there is actually Dorsa recently had a giraffe. I don't know if you have seen that. It's exactly about like the human points at things, and then the robot should understand what it needs to do. I think one nice thing about gaze is like in some tasks, like think of autonomous driving. Like you're not going to point to the direction that you're going to go, but you're actually going to look at there. And so that's one reason. Another reason is gaze is free. Like you just need to track it. Like the information is already there. You just need to track it. So that's another reason. Yeah.
Yeah. All right. Yeah. Thank you very much, Erdem. And thanks everyone for attending.
Thank you.